Okay, let's get cracking. My name's Jim. Welcome to this webinar. We're going to talk about personalized search and recommendations on the Hopsworks platform. And this webinar it's very general at the beginning. We're going to talk about, I guess, the state-of-the-art solution for personalized search and personalized recommendations, which is the two-tower model that builds on embeddings. We're going to look at how to do this at scale. And in particular, we're going to then look at how we do this on the Hopsworks platform. So just a couple of points of order before we start. You'll see that there's a couple of buttons that you can have in Zoom. There's a Q&A button and there's chat. You can use whichever. I mean, Q&A is kind of more organized. We can get them, or if you want to ask questions via chat, that's fine. I'll look there periodically just to see if I can see any questions appearing. Okay, so welcome. So I'm going to talk a little bit about Hopsworks. That's our platform. It's an open source platform for data intensive AI. It's got a feature store in there, and there's also an embedding store coming out in the next version. So it's actually, if you want to play with it, it's on master because it's open source. You can go cutting edge, but we're going to talk about both the feature store and the embedding store today. Now, the platform is an open platform. It's not just open source, but it's got open APIs. You can connect it into data engineering platforms, data science, model serving, data discovery and compliance platforms. And today we're going to talk about personalized recommendations and search, and they're real-time services typically. So you need some model serving infrastructure. We'll talk a little bit about that. You'll need to train these embeddings. You need a data science platform for that. And then you need to get all of the logs that you'll need to use to train your recommendation services or personalized search services, and they'll come from your data engineering platforms. Yeah, it is a feature store. We have a lot of customers. I'll just skip over that. You can believe me. And the platform itself, as I mentioned, is open source. So it's available to be installed on any Linux platform. So Ubuntu or CentOS or Red Hat Linux. And then there's a managed version on AWS and Azure and GCP coming very soon. And you can also install it on any on-prem setup, so VMware, bare metal machines. And we can help you with that with our enterprise version. So yeah, a little bit of where we are in terms of this particular webinar. We're going to talk about the very top end. This is the real-time predictions using your data, right? So real time, so we can consider that to be of a high business value use case in the sense that these are very challenging problems in AI. How do we keep our features updated with very fresh features? How do we have very low latency access to those features because we want to retrieve lots of features? We'll see that particularly in the two-tower embeddings model, it's what we call a fan-out architecture. It'll actually, a single query for a recommendation or for a personalized search will result in hundreds of primary key lookups on the database in the back end. So you really need to have scalable, high performance infrastructure to support these type of use cases. So let's get started, and we'll talk a little bit about the context in which we'll be talking today. Many of you know about machine learning, you know about models and how models can be used, and you can kind of classify models into batch models, so models, analytical models, models that are run on a schedule. And typically the way they work is that you'll have some features, maybe they'll be in an offline feature store, and then your batch program will run. Maybe it's a Spark program, run every day, read up the new unscored values that arrived in your feature store, score them, and then write the output somewhere. Now, if you're doing this for recommendation systems, you might, for example, have a key value store. And I can give the example of Spotify. This is still how they're currently doing it. We'll talk a little bit later about Spotify and some work we've been doing with them for real-time personalized search. But when you log into Spotify, you get a bunch of recommendations, so songs to look up. So what they do is they'll read for every user in Spotify, 100 million plus users, once per day. They'll read up all of the new information or features about the users and update all of the 100 million recommendation lists for the users. If the users log in or not, they don't know. They don't know if you're going to log in or not. They'll still update your recommendations. So even if you don't use it very often, they're going to expend compute, recomputing those recommendations. So this is kind of model that's widely used in industry right now, but it's not the very high-end value model that we're going to talk more about today, which is where we do real-time recommendations and real-time personalized search. So when we talk about real-time recommendations or search, what we need is we need to have a model that's going to run 24/7, an operational model that's going to run online. And that model will take in maybe your search query or maybe a history of what you've done recently, and it's going to give you a recommendation or a personalized response to your search query. So the state that it needs to make those recommendations, it's not going to be available in your search application, not all of it. So Spotify don't know, for example, the history of what you search for, your preferences, you know, what your friends like. It's not all available in the search application. You go to a feature store to get that data, and you retrieve those features, put them together with the search query that the user has generated, and you might have to transform some of these features now. But then that feature vector that you get a result, the array, you send to the model to make a prediction. This is all great. Now, we're going to talk about the two-tower recommendation architecture today, which means we also need an embedding store. We need somewhere we can basically take the query that the users put in, take the features related to that user, so historical features related to the user, contextual features, what songs are cool right now and what songs are not, and we want to retrieve embeddings. We want to retrieve songs that are close to that query that the user has written into the system. And the same for recommendations. So, you know, maybe you've clicked on a movie and what's the next movie to watch? Well, the embedding store will give us back some candidates that we'll need to use that we can rank. We're going to use another model to rank them later on, and then we'll basically return then the recommendations to the user. So the kind of systems aspects that are really important here that we'll talk a little bit about are these services, the model serving, the feature store, the embedding store. They need to be low latency because you're going to do a lot of things before you return your ranked set of recommendations or personalized search responses to the user. And these are operational systems that need to be highly available. Okay, so let's get going and looking at the title of the webinar is Recommender Systems and Personalized Search. So we see them as two problem domains as really one and the same, because what both of them are about is information filtering. You're going to try and take some information that a user is looking for or that we want to recommend and filter it out. We're going to try and filter it out based on the user's preferences, based on their historical interests, based on the context, what's trending, and based on maybe something the user has typed in, like the search query. So some of the paradigms for recommender systems that are quite popular out there are things like collaborative filtering. Collaborative filtering is basically, you've looked at some content, maybe you've read this piece of content, and the system can recommend similar pieces of content. So that's called content-based filtering. Collaborative filtering can also, you can say, well, on the right-hand side, say, this other user read this content that you read. Maybe you should look at that because it's, so actually if you search on YouTube, you get a mix of different recommenders. So it'll say, this is recommended for you, and this is content that was viewed by people who are similar to you. So they're not just giving you one recommender, they're giving you more than one recommender to return your suggestions. There are other types of recommenders, so you can recommend based on maybe a person's social or demographic context. And then you can just take general contextual recommendation algorithms, which is kind of outside the scope of today. So I mentioned the architecture at the beginning, that we have this fan-out architecture, and this is one of the challenges in putting these kind of systems in productions, is that you might have, let's say you're trying to recommend items, and we take songs in Spotify, we have 100 million songs. Well, when a user searches for something, we'd like to take those millions of songs and turn them into maybe hundreds of candidates. We're going to filter down. So we're doing this information filtering stage. So with these hundreds of candidates, we still want to personalize them some more for the user. So we want to rank them based on the user's interests or maybe what they've watched recently. So we're going to look at ranking model for that. And in general, we're not just using the user's history, but also the context of what's cool right now. So ultimately, you're going to recommend maybe a few dozen at most items to a user. And that's basically the architecture that we're looking at today. So it's going to be built on something called embeddings, and we'll try and define embedding to make this clear for everybody who doesn't work in the space. So an embedding is basically a mapping of some discrete or categorical variable to an array of floats is one way of looking at it. So a vector of continuous numbers. So if we take the words in the English language, we've got this thing called word-to-vec embeddings. It's quite a well-known algorithm for taking a word in English, for example, and converting it into this array of floats. So in English, there's about 20 to 40,000 words in common usage. So you can think of it as a categorical variable, the word, and there's 20 or 40,000 different categories. And we're going to learn a mapping from each category, each word, to a point in a multi-dimensional space. And you decide how many dimensions are in the space. You decide how many entries are in this array. It might be 20, it might be 50, 100, 200. But what you'll get is the words will get mapped into this space. Now, what's really interesting about this, particularly if we take language models, that you can basically even do algebra on words. You can say fast plus faster gives me, and then you get an answer of fastest. And there's other ones that have been done. For example, king minus man, queen minus man equals what, and you get woman, and things like that. So because they're in this high dimensional space, you can even have algebraic operators that work on the vectors in that space. Now, the other area where you'll probably have come across what we call embeddings is the area of what we call similarity search. So this is very popular for images. So, you can show a picture of a sunset to Bing in this case, and you can say, Bing, please show me similar pictures. And it'll show you all these different nice sunsets here. And so this is what an embedding is. Embedding is going to map this categorical variable into this dense representation of an array of floating point numbers. And we're able to do what we call similarity search. So we're able to find images that are similar to other images or words that are similar to other words. And we're going to do this for recommending items. We're going to say, hey, I have a recommendation. I have a database of items, and the items could be songs. And the user is going to issue a query. Now, the thing, what we're doing here, and what's new today is the two-tower model, is that when we looked at images and when we looked at words, well, we create this, this vector of floating point numbers for images and one for words, but those two are unrelated to one another. If I have a database of songs, or what we call items to generalize the concept, so if we have a database of items, and then the user's query for these items, so that maybe they query for the songs, we're going to have two different embeddings, one for the items, the songs, and one for the queries. And the queries will have not just the query the user entered, but also their history and context. So the question we have is that, can a user that's entering a query, can it map that query to where the items are? So can it map the query that you have with your context and history into this multidimensional space where these songs are located? Can we do similarity search to find the songs based on what you've typed in your history? The answer is yes, of course, otherwise we wouldn't have this webinar. And we're doing it by mapping the user query embedding into the item embedding space. So we're going to take, when we generate a user query, and we turn it into an embedding, that embedding will live in the same 200 dimensional space, if it's 200 floating point numbers in your array. But basically they're going to end up in the same embedding space, so that we'll be able to search for songs, and the songs will be mapped into this high dimensional space, and the queries will also be mapped into the best matching songs in that space. So this is called representation learning for retrieval, and it involves supervised learning. So we're going to have to look a bit about how we do supervised learning. If you're going to do recommender system, you probably have some system already in place. So users maybe get, when you search, maybe they're given back some items, and the user clicks on an item. So what you want to do is you want to log these, the clicks that the users make. So, in this case, maybe the user clicks on item 3, and didn't click on item 2 or item 1 or item 4. So we can store those clicks, and they can become training data ultimately for our model. So we have to have some way of basically instrumenting our existing recommender systems to collect some training data. We want to know what queries, what did people click on? What items did people click on after they entered certain queries? So how do we create embeddings with a supervised machine learning model, assuming that we can log what the user has done? So one thing you might want to do is find a proxy for your supervised machine learning problem. You might say, well, I want to predict what the next movie a user will watch is based on what they're watching now. And you might think that's great. And YouTube did that originally. It didn't work so well because there was a lot of clickbaity videos were returned. So they then changed the proxy problem to being how long a user would spend watching the next movie they click on. So that downranked to the clickbaity videos. So of course, then you need to log the features when the user selects a movie in order to be able to create some training data for this. Some of the other decisions you need to make is if a user clicks on something and watches that particular movie or listens to that song, but doesn't click on the other items, we call that implicit feedback. So we can store that also as training data. So it's labeled data. User didn't click on this, but they searched for this. You shouldn't introduce too much implicit feedback, because if you have just implicit feedback and explicit feedback, the models tend not to converge very well. So what you also need are what we call negative examples. So often you'll just take random items, connect them to a user query and say, well, the user didn't click on this. And this helps with convergence properties, in particular of the two-tower models. Please shout if you have any questions as well, and we can kind of move into it. So how's this going to work? You're going to select the features firstly to train your item embedding. So the items are going to go into the item embedding space first, and we might have the songs in Spotify, and we have descriptions, names, tags, language, location, genre, price, and so on for the items. And we're going to run them through probably an autoencoder. So we're going to train an autoencoder network, and we'll just take off the decoder. We're left with an encoder, and this produces our embedding. And the embedding is going to be as the size of the embedding in terms of how many floating point numbers are in it. You'll decide when you train your model. Now the user queries, remember we want to map them into the same space. What features do we want to include there? Well, you might include the user's click history. So how often have they clicked on different things, and what have they searched for? How often are they active on the site? You can have static features like the user's languages that they can speak, maybe their location, preferences, an estimate of their age, and so on. So all these features that are historical or that are static or that are contextual about the user, and in particular the query that they're just issuing, you can again make as input features to your neural network encoder, so the autoencoder you're going to train, and then the output will be again the embedding, this user query embedding. Now, how you actually train these, or you can make these slightly more complex, and there's a nice paper from Google that kind of kicked this off from 2019, which was their recommender system. And you can see if we look at the input vector at the bottom, you even have an embedding just for what the user has watched, and another embedding for what the user has searched for, the average of what they search for, where they're from, their age, gender, and so on. And this particular input vector, it's going to basically run through a neural network, and we're going to get an embedding out of there, and from that embedding we can go to a database. We call it an embedding store, and it's going to use an algorithm called nearest neighbor search to look for the top N movies that match. So basically, this is a more complex version. I recommend you to read the paper if you want to get more details. But what we have was this problem of how are we going to train these two embeddings so that they use the same embedding space, so that the items and the user queries end up in the same space. Of course, the embeddings need to be the same length. But what you basically do is if we take the user embeddings and if we take the item embeddings and we compute a similarity metric over them, and it can be cosine or sigmoid similarity. What we're trying to do is we're training these encoders, both the user query embedding and the item embedding encoders, such that the distance or dot product, which is one measure of distance of a user query embedding and the item embedding, when the user has searched for something and their history looked like this, and they clicked on this item, then the distance or the dot product should be low. So the distance of a should be high. Sorry, should be high, I should say. And then when the user didn't click on it, then the dot product should be low. Right. So if I search, for example, for shoes and you show me computer games, well, I should get back a 0. Right. But if I search for heavy metal and you give me back Iron Maiden, then I should get a relatively high response. So that's how they're going to be trained. If you're curious about getting your hands dirty right now, there's a really nice library called TensorFlow Recommenders Library by Google, and it supports training two-tower models kind of out of the box at some level. There's a link down there at the bottom which you can go to see that tutorial. But basically, the training data in their case, they're using the movie lens data set that many of you will be familiar with, and you need to provide the positive pairs. So when the user queried for a movie and the movie that they watched, and you're going to get two models out of it, an item encoder and a user encoder. Now, the point I made earlier was that positive pairs are not really enough for like an industrial strength. You want also negative pairs, and you want random pairs to ensure these models will converge very well. But you'll get a feel for the power of it if you just work through those tutorials. So once we trained our item encoder and our user query encoder, or the query tower we call it, and the item tower, we can see what's happening here. Like, this is a nice visualization from Google that I'll just show you, and I'll walk through it. So the first thing that's going to happen is you're going to train these neural networks, or we're going to train the two-tower model. But then what we have to do is we have to take all our songs. So for Spotify, we're going to run all of our songs through this item tower. It's called the database tower here. And it's going to map all of the songs in Spotify, or books in this case, to this embedding space. Now, so this means you need an embedding store or somewhere to store all of these embeddings. And then when you want to query, and here it's querying Shakespeare tragedy, you can see that it ends up very close to Romeo and Juliet and King Lear. So the query tower places that particular query string, Shakespeare, very close to the two Shakespeare books. So the books were Romeo and Juliet and King Lear, I believe. Yeah. So we'll see that then. So now we're just populating the embedding space with the items, and then when the query comes in, we can see Shakespeare tragedy. It gets mapped very close to those. So approximate nearest neighbor search will enable us to find these books and return them as recommendations. So what we saw there was that we do need an embedding store. Now, there's a bunch of embedding stores out there. It's a really exciting new space. I guess the most well-known contribution in the space in recent years was Facebook's library called FICE, and it uses hierarchical navigable small world graphs to provide order log n search for items in this embedding space. So it's doing approximate nearest neighbor search, and you can see the way it works is that it starts out, at layer 2 here, and then it sort of navigates the space using this hierarchical small world graph network algorithm, and then it finds when it gets to the bottom of the graph, it basically then returns the nearest neighbors in that space, part of the space. So an embedding store is basically a way of durably storing these embeddings, so that if the system shuts down or if it goes offline, the embeddings are still there. It has an API for supporting similarity search, and of course you need an API to then index or write these embeddings to the embedding store. So Google has another library called Scan. Both of these libraries are quite popular. The Scan is quite recent, seems to be quite high performance. But there's no Google have they have I think a managed database that runs on Scan. But FICE, there's a bunch of different systems out there. There's Pinecone, and then there's a bunch of other open source embedding stores that are basically layered on top of FICE. And one of those is in fact OpenSearch, which is the new fork of Elasticsearch by AWS. So it's an open source version of Elasticsearch. It's managed by the development is primarily driven by AWS. There are other vendors contributing. And for OpenSearch, there actually is a plugin called KNN, and the plugin KNN provides the ANN index in OpenSearch. So we get an embedding store in OpenSearch. So what we want to do in our platform, Hopsworks, is we're supporting OpenSearch KNN plugin on our platform. So what you can do is, if you had the entire library of Spotify songs, well, you could have your item embedding model that you've trained already, and it can read up all of the songs in Spotify and all of the features that are needed to compute the embedding from the input features, and then you insert all of those embeddings, and you'll need an ID, of course, to be able to uniquely identify each embedding, and you're going to write them to this approximate nearest neighbor the nearest neighbor index in OpenSearch. We'll have a look at some code for doing that. You can also do other things. You can add additional attributes because it's OpenSearch, which is nice compared to other embedding stores, and you can filter based on those. So you could say, for example, whether a song is suitable for children or not, and then you could filter out songs because they're not suitable for minors, for example. So that's a really great capability you get for free because OpenSearch supports, obviously, filtering, and many of the new embedding stores don't. So let's have a look at what this looks like in terms of code. And this is showing a very, it's not a Spark program here. You can see it's just a REST call. So we're doing a HTTP put to put into an index. So these indexes, OpenSearch supports data is stored in indexes. Think of them as being, if you have a MySQL database, it's like creating a database, and index is like a database. And in this case, in the index, you can see that we have some settings for an index, and if you're curious in the documentation, there's a ton of different things you can configure in the index, including memory space and things like that. The type of the space is one of them. So we talked already about the distance between the user query and the item query, and cosine similarity is the default, but you can actually change that. You can see we're using k-nearest neighbors as well. There is support for exact search, but that's not very good performance. So typically approximate search is what you'll do. So what we're going to do in this particular index is we're going to have two vectors supported in here. One is called the KNN vector, or sorry, my vector 1, and the second one is my vector 2. And the first one is a very small embedding of length 2, and the second one is a small embedding of length 4. So reasonable lengths are 50, 100, 20 sometimes, or even 200, depending on your problem. So this is how you create the index, and then we want to populate the index. So, typically it would be something like a Spark program or a Python program that will make this HTTP post operation. And there's an API, Python API for OpenSearch that makes this easier. You don't have to write, this ugly code. But what you're doing when you're inserting items into the index, in the KNN index in OpenSearch, is that you basically identify the name of the index. So we have two indexes, remember. One of them is called KNN index 1. And we put in the actual, the vector. So this is our embedding. So the embedding has two values, 1.5 and 2.5. And you can see we added an additional attribute here called price. So we didn't have to add price, but we added it because maybe we'll like to, filter on price as well as find the nearest neighbors. You can see every row in this index has a unique ID. You can see we've got a 1 to 9, or 8 actually is all I fit on this page. And you can see then for the second vector, my vector 2, that the array is now length 4. So it's no longer the embeddings aren't of length 2, they're length 4. So this is basically how you write your data into the index. When you want to query from this embedding store, what you do is you basically issue a HTTP GET request. Again, there's library support for this. And then you can specify the size. And this size option here, it indicates how many results you want the query to return. So we'll see later on that for Spotify, actually for personalized search, we're looking at 250. So it's going to return quite a lot of potential songs that you want to display to users. So here we can see here that we place in the input, which is the input embedding. We say the number of k is the number of neighbors the search in each graph will return, and then the size of the actual. So because remember, you're going to k nearest neighbors means search this many neighbors, but then the size is different. That's the number of values we're going to return. So yeah, so in this case, you might do k nearest neighbors to search a wider set of neighbors. And remember, it's approximate, but then you might say, well, I'll search for 500, but only return 250. And because it's approximate, it'll look at the 500, but then it needs to figure out of those 500, which ones are the 250 closest ones. I mentioned already, you can use your attribute price, which is nice to do filtering. So this is a query where we add a filter. So we can say, I want to search for, the 2 closest neighbors. Here's my input embedding. We're going to do similarity search, but please, after you've returned the 2 nearest neighbors, filter out any return values where the price is greater than 5 or less than 10. And if filter out means don't include them, that means ultimately we'll only get candidates with a price between 5 and 10, because it's greater than or equal, it's not just greater than, the same with less than. So once you've gotten back your set of candidates, you do have to rank them, because what happens is if you just take the results from the similarity search, you tend to get very similar recommendations. So often what you want to do is you want to add some diversity to the set of recommendations or search results that you want to return. So what people tend to do is they tend to have a re-ranking or a ranking model, which will take the 250 items returned and re-rank them. And you can and typically this can be a machine learning model. Typically it's going to be a fast one like gradient boosted decision trees. You need to decide what features to include in this model, because if we look back at the previous example, we only had back the ID of the, you can see when we return the value, we're only going to get back this, the ID of the particular embedding, the values for the embedding, and then the price attribute. So with that ID that we get back, that ID should map to, for example, a user or maybe an item I'm looking for. And with that information, what we can do is we can go to a feature store again, and the feature store can give us features for that particular user or item. And those features we can include, things like demographics, price propensity, metadata of items. We can use those in our gradient boosted decision tree model to rank the items. So it's going to use the feature store to enrich the candidate features. And there's an example for building a ranking model with TF recommenders linked here below. Now, the other stage I mentioned already was filtering. So, if you go to a web page and you look at books and you get some recommendations, you can see there's this button appears, so sci-fi, short story, space opera. And then for summer outfits, you can refine your search. So these ways of refining them, they're tags, they're metadata. We can see that we can add these attributes into OpenSearch, but the problem with that is it's just going to filter out the results that were returned. It's not going to generate new results. So there's a couple of different ways you can work with these filters. We saw already that in the embedding store we can have these static attributes, and we filter out the approximate nearest neighbor results. Other things you can do is you can actually add these tags as features to either your user query or item query, and then this will help then when the user presses the button, it'll rerun the recommendation request, but this time have the tag set. So then when you get back the candidates from the embedding store, they should either be closer to this particular category or class of items that you're interested in. And you can also then, of course, use the feature store to retrieve tags or for your ranking model. So you can go and say, okay, well, the user clicked on this, so I'm going to re-rank with this new category that the user clicked on. Okay, please, if you have any questions, just shout and we can kind of take them from there. So, how do you design your filters? How do you design your tags? Well, there's no, we saw that there's different ways you can do it, and you have to curate them, you have to manage them. Are they going to be in the models or in the metadata? There's a lot of decisions you have to make about these tags. So I won't go into too much details about that because it's a whole research area in its own right. So let's have a quick look at how we implement this kind of architecture in Hopsworks. So Hopsworks is an open source platform. All of this is open source. It's also a managed platform on AWS and Azure and soon GCP, so you can kind of put it all together. But if we look at this, the online infrastructure that we need to do this retrieval and ranking for recommendation, personalized recommendation search, if somebody is watching a movie and we want to recommend the next item, well, firstly, we'll take as input the movie the person is watching, and we'll then get their history and the context and so on, and we'll run it through our user query embedding model. And then we'll go to the ANN index so we can look at the actual technology that we need. So the first thing we need to do actually just to build our embedding model is we need to go to the feature store, because we need to find the history of the user and the context, and that won't be in the application here. So we're going to do that, and then we're going to build this embedding. The embedding is going to use an embedding model. Now, your embedding model could be embedded inside your application. It could be part of your application. You could read it up, or it could be served over the network. So you could be using a model serving infrastructure like Kserve or SageMaker, and that means a network round trip. Okay, but that might be the benefits of managing your models separately from your applications might mean that you'll take that hit on the network round trip. So now we've got our embedding. We make a query on the embedding store. Again, that's going to take a few milliseconds, and it'll return our candidates, maybe a couple of hundred. And then for those 250 candidates returned, if we have 250 candidates returned, we're going to, for each one, we're going to have to go to the feature store and get new features for them. We're going to have to enrich all of those candidates with features because we want to use those features to rank those candidates. And again, that model can be served or hosted over the network, or it can be embedded in your application. And then finally, once you've re-ranked these candidates, you return them to the user as recommendations. So we can see there's a bit of infrastructure, and all of this is available in Hopsworks. We have a feature store, we have Kserve as our model serving infrastructure, and then we have this embedding store built on OpenSearch. So you also need offline infrastructure. It's not enough to have online infrastructure, and offline infrastructure is needed to train the models. So we need to train the user and item embedding models. We need to train the ranking model, and we also need to be able to populate, for example, the embedding store, approximate nearest neighbors index for our items. And you can do that, for example, in Spark. So all of this is possible in our platform as well. You can, for example, have feature engineering pipelines run on our platform or on any external Python or Spark environments. So if you're using SageMaker or Databricks, that's fine, keep using it. But you can also run these jobs on our platform, and they'll create your features. Features will be used to train our embedding models, the 2-tower model. And then we deploy those models to model serving infrastructure. So we deploy them to Kserve. We can have a Spark application run on our platform that will take, for example, all of your songs and run them through the item, in this case, the item embedding model, and write those embeddings to the embedding store. And we may have additional attributes that we want to add to them because we want to filter, and we can do that at this point in time. So we're building the index and embedding store for the items. And then we'll also need to train the ranking model, and the ranking model needs to be fast. And often, gradient boosted decision trees and decision trees in general, random forests are popular for that because there's not going to be a huge number of features, right? And, so let's look at what this looks like in Hopsworks in practice, and what a service, a personalized search or recommendation service looks like in practice on Hopsworks. So firstly, you'll need to have a service. So this could be a microservice that you write. You could write this, for example, in Python or in Go or Java, whatever you like. Our platforms support, well, Go is not great because we don't support native, native APIs for Go, but we have native APIs for Python and for Scala, Java. So what will happen is, let's assume it's a Python service, for example, the user will issue a query to your Python service. It's a microservice that you write. And the query comes in and we'll have a request ID associated with it. So what we're going to do in your Python program, you're going to make an API call to the feature store. We have a library called HSFS, and you'll say, okay, here was the query that came in. Here's the user ID, maybe the associated with this query. Retrieve the user features. They might be historical, give me any contextual features. I've got a bunch of features now. What I need to do is compute the embedding for this user query. So you send then the input array to the model. It's going to go maybe over the network if you're going to host this model over the network in Kserve, which is probably a good idea because you're only going to pay like a 5 millisecond latency overhead for that, for example, maybe 5 or 10, and now what you'll get back is the actual embedding. So your input features came from the feature store. It's going to cost you maybe 5 milliseconds or 2 or 3 milliseconds, 10 milliseconds maybe to get back your embedding. Then we go to the embedding store, OpenSearch, the KNN plugin, to retrieve our candidates. And if we're doing the song example again, it's going to return 250 candidates. It'll be another 20 or 30 milliseconds. So the next stage is actually a real fan out stage, which is something I'll talk a little bit about what we did with Spotify. We get 250 candidates returned, and for each of them, we need to go to the feature store to get the features for all 250. So that's going to be a batch primary key lookup on the feature store. It's going to say, here's 250 primary keys for these items, the songs, give me back all the features. And if you want to do it again for the users, you can do that as well. But you'll have some user features already in this service from earlier in the query, so you probably don't need to re-retrieve them. So we can do that in like a P99 latency of 30 milliseconds. So finally, then we're gonna rank the models, and this might be done embedded in the application for performance, or you can do it over the network. You need to parallelize it because you're doing maybe 250 of these rankings. So again, another 30 milliseconds. So our end-to-end latency budget here might be about 100 milliseconds by the time we get back our ranked results. But you can see there's huge activity going on in the back end to get there. Now, when a user finally selects an item of the ones that are recommended, that's important because we want to save that. It's a positive outcome. We want to log that back to the feature store. So that's also possible in our platform. Okay, so the platform that you need for this, you don't need to have compute, but it kind of looks like this. We have support with the feature store where we serve these features online, and you have access for historical features for creating training data. So you can do model training, use a model repository where we can store our models, we can serve our models, and then we can log the requests that are made to the models back to the feature store. And then, of course, you can have your compute, which is computing the features and the feature pipelines. It can run inside the platform or outside, and it connect to many different sources, from batch streaming to even microservice HTTP sources. So this is basically all you need to kind of put this whole thing in practice, and this is available in our platform. And of course, it's an enterprise platform, so there's governance and access control and all that good stuff. So I mentioned I talk about the Spotify use case. So I'm just going to go through it briefly. And there is is there a link here? Yeah, there we go. So there is a reference at the end for this. So basically what they're looking at doing, and it's not out yet, but it's still at an early stage, is support personalized search using the ranking retrieval architecture. So in their case, they need up to 6 million operations per second on the feature store. And they need to have very good latency bounds on these batch lookups of our, let's say, 250 candidates returned from the embedding store. So they basically looked at two databases to act as a feature store, one called Aerospike, which is a key value store, and then our database for our feature store called RonDB. Many other databases you might consider, like Redis, which is in memory, and it's quite good performance, but it's single threaded, it doesn't scale out, and it's not a database. So if your nodes crash, you don't have any node level recovery or system level recovery. Unless you go to enterprise Redis, you might get some of that. But
just one question in the Q&A.
Oh, we have a question here at this point, right? One advantage of feature stores is they allow us to reuse features. Does this apply to embedding stores too? Are embeddings more use case specific? Thank you, Mr. Or Mrs. Anonymous. They're not reusable. Okay, I mean, in principle they are reusable, but like, if you're computing embeddings for a very high value use case like personalized search for songs, how many other use cases will that be available for? Maybe if it's I don't know, but it's not one of the motivations in any case for an embedding store. The main reason people decide to go with an embedding store instead of just having a library, a FICE library or a scan library and a Kubernetes application that can be scaled up and down, is because you might have a lot of data and you have high availability guarantees that you need to give. So you want this service to be up 24/7. And if, for example, your Kubernetes cluster goes down, you've lost your entire index and you have to rebuild your index and you're gone for a long time. On the other hand, if you're running OpenSearch, a server can go down, the system keeps running. And if the whole thing crashes, you can still, recover from disk. OpenSearch is not as good as a database in terms of system level recovery. There can be cases where small amounts of data can be lost, but in general, you can just recover it. In this case, in the case of an embedding store, losing some item embeddings and repopulating them in the background later is not a big deal for most use cases. Okay, so I'm just going to talk a little bit about this really high-end use case, the Spotify's personalized search. So RonDB is our database we developed. Mika Ronstrom is the main developer behind it. It's a fork of MySQL cluster, NDB cluster. It's a very mature database, been around for 20 years. When you turn on your phone, most likely you're using it. It's because about half of the back-end databases behind network operators, these home location registries, they run NDB. or RonDB, which is our forks name. So some of the nice properties of it is that it has these 4 particular characteristics. You get high availability, which is very important, high throughput, 6 million operations per second, low latency, so 250 batch key lookups in 30 milliseconds, and then you can add nodes to scale it out. So you can scale to even petabytes of capacity. I'm not going to go through the details of the benchmarks, but we benchmarked the platform against Aerospike, which is quite an expensive enterprise key value store, and it's probably the best one out there after RonDB. So RonDB is still currently probably the fastest for your hardware key value store available today, but it also has a nice SQL API, which makes it a lot easier. So what we can see here is that, you know, for if we look at say RonDB, you know, we're getting 2 million operations per second, so higher is better here because it's throughput, and we're getting, you know, quite a bit lower for Aerospike on the same hardware. And then for latency, you know, higher is worse. So you can see that for RonDB, you know, if we look at our throughput's higher, but the latency is quite similar, I guess, for most of it to Aerospike. So you have very high throughput, which is 8 concurrent clients. They're similar-ish on latency. RonDB is slightly lower than Aerospike when the load is higher. But the interesting thing here is that, you know, even with 2 million concurrent operations per second on just a few database nodes, this is 6 database nodes, the P99 latency is under 40 minutes, 38 milliseconds or something. So, you know, 35% higher throughput, 30% better latency, and it's open source to boot. So I'll just show you briefly the platform. We got a couple of minutes, and I wrote some code for how to use OpenSearch. So this is the platform here, and you have these. This is the feature store. You can have feature groups. You can see, you can browse them. It's a registry. I can search for them. Search here. And this is actually using OpenSearch in the background to search for those. And then we have training data sets. We can run jobs in here. You know, if I go and look at this particular one, all right, it was another project. So we have these things called projects. So I was in this project here running a notebook. What we can do is I'm actually running a job that's a Spark job that's writing to OpenSearch. So it's populating an index here. And it looks like this. So I showed you some REST call before, but this is much nicer. This is just reading a CSV file into a data frame in Spark. It's using actually an Elastic connector. So not OpenSearch doesn't have all the connectors. It's still compatible with some of the Elastic connectors. So then what we're doing here is we're just writing that data frame into OpenSearch. And then we can read back that data frame. You can see it looks like that. So it's all pretty straightforward. You know, what we actually do when we run jobs is we also store the logs. I was going to show the logs here. Server logs, maybe it's here. If we get some server logs in here. So you can see OpenSearch is powering all of the logs in our platform. So these are application logs or logs for Jupyter notebooks or whatever. Okay, so that you get a feel for the platform. If you want to try it out, you can go to www.hopsworks.ai. It's free to register and play with the demo cluster. You know, if you want to use the kind of managed platform, what you need to do is you need to connect your account. So you need to create what's called a cross account role in AWS to connect our cloud account with your cloud account. And for Azure, you need a tenant ID and subscription ID. But once you've set that up, then you're able to actually just create a cluster on AWS or Azure. And I created a couple earlier on. And these are nice. One of the nice things about the platform is the clusters are elastic. So you can add and remove workers. DB cluster in here as well. It's a small cluster with just a single node. And you can even have auto scaling. So it'll only, you know, allocate workers when you need to run the services. The data for this is stored, for this cluster is stored in S3 on AWS and ADLS on Azure. So it's in object storage, and you can stop and start these clusters. So you only pay for what you use. So we'll track your usage here, you know, and it's a really great way of just getting, you know, started and playing with the platform. So that's pretty much it from my side. You know, we're at the end of the hour. If you want to find out more, you can go to hopsworks.ai. And reach out to us. There's also a community webpage, community.hopsworks.ai. And if you have questions in particular about, there might be another question here. That's the same one I answered live, okay. Then please go and ask on community.hopsworks.ai. Thank you everyone for attending, and have a great rest of your day and rest of your week.